taking a look at refraction at a spherical surface. And just for simplicity, I'm actually going to create a spherical surface bending in this direction. And we're not making any assumptions about the medium on either side, other than that on this side of the sphere we have index refraction n1, on this side n2. And the circle has a center right here, and radius of lowercase r. Now, we're going to go ahead and place an object at, say, this point right here. Call that our object. And then we're going to draw some rays coming out. So one of the rays that's going to come out will be horizontal along the optical axis. That optical axis is essentially the symmetry center of our system. So as it's coming out, when it hits the surface, it's hitting it at a normal, and so it will not bend. The angle of refraction is 0 if the angle of incidence is 0. And so that comes out like that. And consider that where this ray looks like it's coming from. In other words, if we go ahead and we were to be looking with an eye down that way, it looks like that light ray is coming along the center line. And that's going to be important in terms of locating our image. Now, take another ray from our object point, and I'm just going to shoot it up here to where I've drawn the radius. And the reason is the radius defines a normal at that point. And so let's go ahead and assume that in this case, the ray actually bends towards the normal. And so this angle right here is theta 2. And the angle inside here is theta 1. Now, the ray where it looks like the refracted ray is coming from, in other words, if we have an eye out here looking towards where that light ray came from, it looks like this light ray came from back here. Now, where the two rays cross, the one that went out this way and the one that's going out this way, where those two rays look like they cross, that's where my image is going to be located. So in this case, I have an image at that point. Now I just need to define a couple of other things. I'm going to define the line H right there, which is the height from where this light ray hits the lens to the optical axis. And the other angles I'm going to need are this angle with respect to the radius that we're going to call gamma. This angle with respect to the apparent ray for the refracted ray is alpha. And then this angle that the ray from the object makes, we're going to call that phi. I also need to define a couple of distances. So the distance between the object point and the surface of the lens, we're going to call that SO. That stands for the distance of the object. And the distance between the image and the surface of the lens, in particular this point on the optical axis, we're going to call D. Now, one assumption that we end up having to make here is that this distance right here, which I'll call delta, that distance needs to be small relative to all the other distances that we are making. And this really comes down to what is called the Paraxial Approximation. What this means is we are going to go ahead and assume that the angle that our rays are making relative to the optical axis are very, very small. So the way I've drawn it here is very exaggerated. If I go ahead and draw things a little bit more the way they should be, this is what we would see. This outgoing ray right there is making a very small angle relative to the optical axis. And so this really kind of comes down to either assuming that our theta 1 is much, much less than 1, or equivalently, we could say that all of the distances that are involved are much, much, much less than that height h. And that's going to come into play because we're going to use the small angle approximation for one of our steps. All right. The other thing we should do is see if we can relate the theta 2 that's outside to one of the internal angles. And so this angle right in here is actually the same as theta 2. Now, let's take a look at one of the triangles in particular. This triangle that I've sketched right here is the same as this triangle right there. And so the interior angles have to add up to 180, which is how I can find this angle right here. But the other thing to note is that this is a 180-degree angle, so 180 minus phi has got to be equal to this interior angle here, and so I get a relationship between phi, gamma, and theta 1, which I will rewrite as this, because theta 1 and theta 2 are what we're going to need for Snell's law. Then I'm going to draw this triangle here that involves gamma and alpha and theta 2. So if we go back to our original drawing, we'll see that this is involving gamma, alpha, and theta 2. This is this guy right here. So again, we're using a similar argument where the interior angles have to add up to 180, which is how I get 180 minus theta 2 minus gamma is that angle. And we're going to use the fact that this is 180 degrees, so 180 minus alpha equals that angle in there, and I end up with this relationship between theta 2, alpha, and gamma. Now we're going to use Snell's law to find a relationship between theta 1 and theta 2 at the surface, and because we are assuming that theta 1 and theta 2 are very, very small, much, much smaller than 1, then we're going to do the small angle approximation, which is that the sine of theta is approximately theta. And then we're going to go ahead and plug in this equation and this equation in for these guys, which gives me a relationship between phi, gamma, and alpha and the indices of refraction. Now I'm going to make use of the small angle approximation again, and let me just go back to the original diagram and see where this triangle lies. This is the angle involving alpha and then side h. So on my diagram, that corresponds to this triangle right here. And using the small angle approximation, I have that alpha is approximately tan alpha, and tangent of alpha is opposite over adjacent, and so I get an equation that relates alpha to h over d. I'm going to do the same thing with gamma. Let's go take a look at where this diagram came from. So this is gamma, and that's going to be this triangle right here. And we do the same sort of thing where gamma is approximately equal to the tangent of gamma, and the tangent of gamma is h over the radius. And then finally do the same thing with phi and h. And that triangle is this guy right here. And so phi is approximately tan phi, and then we can use the sides of the triangle to find the tangent. So now we're going to plug those approximations into our approximation of Snell's law, and we get this relationship here. Or rearranging things a little bit, we want to make things look a little bit more like the case that we got with the spherical mirror surface. And we get this equation right here. Now we're going to follow the same sort of sign convention we did And what we're going to assume is that S sub I, the image distance, is actually the negative of D, and the radius of curvature is negative R. This has to do with how we're defining signs of positive and negative curvature and positive and negative image distances. And so with those two pieces of information, we can go ahead and plug it in, and this is the result that we get, which looks fairly similar to what we got with the mirror, with the biggest difference being the introduction of the index of refraction. Now, I do want to just take a look at what happens if we have an infinite plane. And in the case of an infinite plane, the radius of curvature, r in that case, is infinite, which means that this second term right here is going to end up being 0. So let's take the example of, say, a fish located at the object position, and then the image is going to be here. Where exactly is the image relative to the object? Well, we can solve this equation up here for the image distance, and this is the result that we get. And so let's go ahead and plug in our numbers for a fish in water, and 1 in that case would be 4/3, and 2 would be 1. And so what we get for an image distance is that it's going to be negative 3/4 S naught. This is one of the homework problems that you had to solve in a little bit more detail. The only difference here, of course, is the minus sign, and the minus sign is coming from the fact that we assume that positive image distances are on the far side of the interface, whereas negative image distances are on the same side.